probability of us finding a particle in a given location under certain potential. Now, if we are having a speck of wave function at this side of our graph, at this side of our potential, it means that there is a slight probability that we might just find this particle over here too, on observation. Before observation, it's everywhere. It's literally everywhere. In fact, everything is everywhere. Even I am being a macroscopic body. I am here, I am here, I am here, and there is an infinitesimal chance that I'm on the moon. And no scientist can negate that until he observes me. When they observe me, my wave function collapses. Anywho, that there is this transmission probability that denotes the probability of this particular wave function, and it can be get by solving your Schrodinger's wave equation quite orthodoxically, and we get this as transmission probability to be e to the power negative 2k2l, where L is the barrier width, like this width, and U is, and K2 denotes this thing, where U is the energy of the barrier, the height of the barrier, and E is the energy of the particle that is being passed out. And M is the mass of the particle moving out. Okay? Alright, so what does that have to do with our nucleus? What does that have to do with our alpha particle? As it turns out to be, the nuclear diagram of an orthodox nucleus is just like that one. But then there is a trick to it. Now we can see that the barrier's height is greater due to a resolution problem I think that you might not be able to see, but I wanted to show you all. But anywho, you see the particle, oh crap, baskets.
You moved this one.
Yeah.
You can, okay. Can you, is it, should you sit down?
Yes, ma'am. मैंने सुना था.
Yeah, so if you were to look at this diagram,
Call करते.
you see that the energy of the alpha particle that is being emitted out of our nuclei is usually at the order of 4 to 9 megaelectron volts. But the energy barrier has the height of 20 to 24 megaelectron volts. So now this is analogous to the thing that I have just told earlier in the previous slide. But the nuclear potential diagram is really different from the one that we saw earlier. You see, the nuclear potential diagram that defined our transmission probability was kind of like this, where the height of your barrier was U, the length of the barrier was L, right now, and the energy of the particle that is trying to escape the barrier is E. Alright? Now, there is a certain probability that it leaves an evanescent wave out of it, and that probability is T is equal to e to the power negative k2l. Makes sense, but does this thing that I just drew, does this look like that? No, it doesn't. So what should we do? We should go for maths, because maths is strong and we should use its strength. Alright, so I will borrow some techniques from my good buddy Newton and his calculus. Now, you see, it's really easy. I just turn this curve that is being deteriorating as 1 by r linearly into small rectangles, infinitesimally small rectangles having their width equivalent to dr, and then add them all continuously between r and r naught, where r is the radius of the nuclei and r naught is the energy of the Coulombic force, is the point where the energy of the Coulombic force turns out to be equivalent to the energy of our escaping alpha particle. Alright, makes sense, but how would we do that? Well, maths, of course. Well, you see that derivation, it's beautiful, it's amazing. And well, this is the, the nutshell kind of a thing of our derivation. At first we take, you see, at start our expression was this one. T is equal to e to the power negative 2kl. Now, we have integrated it. First of all, I have taken natural logarithm in order to avoid writing everything in exponents. It's very tedious. So we have taken a natural logarithm, and with this we get ln of t is equal to integral of r to r naught minus k2 into dr. What was k2? We have defined it earlier to be k2 is equivalent to square root of 2m into u minus e divided by h bar square. Right now it was kind of like that. Yeah. Well, it is what it is, k2. We plug in that value and then we solve that integral. Now that integral is a little difficult to solve. In fact, when I solved it, I had to substitute its value 11 times to get the solution. Now, if you want me to do the derivation over here, I love maths, I love doing derivations, I can go for it, but it's up to you guys. So
I think you can go with the main equations and the exponent.
yeah, the main equations are written over here.
Yeah,
the
that's
derivation is beautiful. Doing them,
That's in the paper, right?
yeah, that's in the paper, the
Yeah.
one that I sent you.
Yeah. If you have a question, you can ask. Okay.
Yeah, you
And-
can ask anytime, but that anytime will start once I end this.
Okay. So, yes. Okay. So you can
Alright.
proceed.
Okay, but so at the end of the day, we get this thing. And although it's an exact equation, it tells you about the exact transmission probability in a general term, like no matter what kind of situation you have, you can explain it. You can explain that using this little formula. But only problem is that it's not little. It's big and tedious, and no one wants to memorize this thing. At least I won't. So we can do something, as Dr. Woodward always used to say, physics without approximations is almost impossible. If it makes your work easier, you can go as bizarre as pi is equal to e is equal to 3, SUNY if you don't like it. So, what we do over here is that at first I would apply the binomial expansion by declaring that r is r naught is very less than r. And with this, my expression will shrink up a bit. And after that, I will substitute the value of r using this one clever trick, and it's beautiful and very classical in nature, not hi-fi as everything has been ever since I started speaking. We know that E is equal to 2 ZE square divided by 4 pi epsilon naught into r. Right now, everyone knows about it. But what I will do is, I will shift their places. And I will get r to be equal to 2 ZE square over 4 pi epsilon naught into, E. So rather than having the radius, the distance as a variable, rather than having that distance as a variable where your Coulombic potential is equivalent to the energy of an escaping alpha particle, it's very difficult to solve. Not that with that kind of a variable, we have a rather easier variable, that is E. And we know the energy of the escaping alpha particle. So we will plug that value into that expression after applying the binomial expansion, and we will get, and then by applying the values of all the constants that are present in that equation, we'll get this beautiful this beautiful formula. Like, I'm in love with that formula. That states that the natural logarithm of your transmission probability is equivalent to 1.29 into z power 1 by 2, or not power 1 by 2, minus 1.72 ZE power 1 by 2, where Z is the atomic number of your nuclei, R naught is the radius of your nuclei, Z is again your atomic number of your nuclei, and E is the energy of your escaping alpha particle. Now you see the similarity with the Geiger-Nuttel's law? Well, that law was actually not devised mathematically, like taking your assumptions and doing the maths over it, just like orthodox theoretical physicists do. It was actually by meticulous experiments we found out that there is this particular trend that our nuclei follow while decaying using alpha decay.